3.2, number 74. So we have a piecewise defined function, and it is 2 root x as long as x is between 0 and 1, and it is 3x minus 1 as long as x is greater than 1. And we're supposed to sketch a graph. So when we sketch this graph, the main thing they want us to note, it would seem to me, is that the function is continuous. At this location 1, where it switches from acting like 2 root x to becoming 3x minus 1. They're trying to demonstrate a particular type of non-differentiable location here. It may not be obvious when you're first doing the problem, but just as a heads up, that's kind of the goal they have. All right, so if I start to graph this, then between 0 and 1, right, between 0 and 1, from the origin and 1 here, the function looks like 2 root x. So a common way to graph these piecewise defined functions is just to take the endpoints of the interval that's applicable to that piece, so 0 and 1, just plug them in. So we have 2 root 0 is of course 0, so we have a point here that's on the curve, and then you have 2 root 1 is 2 of course, so 1 comma 2 here. All right. And we know what the root function looks like as a parent function, so all I got to do is draw a reasonable curve here. Something like that. In theory, of course, it would have gone on forever this way, but because it's piecewise defined and only applicable in this smaller interval, I only need to draw it for that small portion. All right, so that takes care of the first part of the function until you get to 1. Now, after 1, it's going to look like 3x minus 1. 3x minus 1, linear, of course, and has a y-intercept at negative 1, which would be, just move this a little bit, would be down here. I don't need to draw that per se, but it would be right here, of course. I'm just going to put something there, even though it's not really on the curve, just to guide me as I draw this. So then I would go up 3 units and write 1 unit from that location, and that would put me another point on the line. So I'll go up 3 units, 1, 2, 3, and over 1 according to the slope here, 3 versus 1. And it turns out that I landed right on the point where they're gonna connect. So the line would look like that, right? Going up from this location up through that point where they happen to connect. Again, because from my perspective, they're trying to show you a continuous location which is not differentiable. So if we keep going up by 3 and over 1, right, it would continue to look like this, something like that. All right, so this part, of course, is not really part of the curve. I'm just using it as a guide to get that this ray drawn over here, emanating out from this point where the two pieces connect. So maybe something like this. All right, I'll just leave it like that. That should be good enough. So the main thing is, if you notice the way the curve looks, again, continuous. Continuous, but not differentiable. And the reason it's not differentiable is because the slope suddenly changes value there. That's the essence of a cusp. Okay, you can kind of see it here, right? The tangent lines, right, would look something like this. There's one, there's another. So right when you get to this point, it's looking something like this. And there's a tangent line coming from the left, right? And then there's another tangent line coming from the right of one, right? And it always looks like this slope here. right? It's always the line's slope of 3, so it looks like that. The tangent line is actually the same as the line, this ray, this line itself, 3x minus 1. That's the way it is for all linear functions. The tangent line is the same as the line itself. Anyway, the point is that the two tangent lines, the one coming from the left, the red one, is not equal, its slope is not equal to the one coming from the right, the blue one, and so therefore you don't have a well-defined slope there, because it's two different values, one from each side, so therefore the overall derivative will not exist.